Hello. So we're going to talk about probability on compact groups today. So that's the last lecture from the series on matrix groups. So we'll compute laws of characters and truncated characters too for the most basic groups. It's an introduction. I mean, the subject is really huge probability on compact groups, and what we're going to do today is the most basic computations that that you can do. So let's find this presentation, probability on compact groups, as I was telling you. So the subject, yeah, it's really big, and we'll be just interested in this very modest problem to compute the law of the main character. Okay, I've seen already in the previous lectures that this is an interesting question. So yeah, that's going to be it. Compute the law of the character with respect to the uniform integration, hard measure. So the motivation somehow it's, well, the moments of chi are very important things. By Peter Weil, these are the dimension of the fixed point spaces of the Peter Weil representations. Peter Weil representations means the tensor powers of pi and pi bar, pi being the fundamental one. There's a comment here, we're actually interested not exactly in these fixed spaces, but more generally in the Tannakian category, home spaces between pk and pl. You see fixed points is when you put k is 0 here. I mean, here it's a home of 1 in pl, that's fixed points of pl. But by Frobenius, we have identification. I mean, these guys are fixed points. So you see home pkpl is fixed of pk bar l. K bar means to reverse the word and change black into white, I went into black. I remind you, all the exponents are colored here. White corresponds to pi, black corresponds to pi bar. So finally, what we're computing here, these moments, they compute all the dimensions of the spaces of the Tannakian category. So these are the most important invariants, the very first ones of your group. So of course you can say that by using this law instead of the moments, well, the law is much better because you like to get into probability, and actually we'll see for the most basic groups. Symmetric orthogonal, we get Poisson law, Gaussian one. So it's definitely, these laws are much more basic objects than their moments. So that's why we use laws instead of just moments. Now, more generally, now we'll be interested just a little bit, although beyond this level, we'll be interested also in the truncations of the main character with respect to a parameter t. Why? Because this is very natural. Let me tell you what happens for the symmetric group. So that's something that we've seen a few lectures ago. So chi becomes Poisson of 1 when n goes to infinity, and chi t becomes Poisson of t. So this is very nice. I mean, we have a convolution semigroup there. It's very, very natural, and well, it's a random matrix ideal. It's important, okay? And actually, for solving the problem, we'll have to do substantially more, to develop substantially more techniques than solving problems for characters. So it's very instructive. So this is what we want to do. Compute all of the character, also these truncations. No, well, let's start with finite groups. This is fun, and we already did more as the work, but let's remind all this with a few more things. So for the cyclic group, regarded as cyclically permuting, right, the coordinate axis, there are no fixed points, right, except for the identity. So you get a Bernoulli law. It's concentrated at 0, and the identity contributes here with a bit for delta n. And well, truncations are not interesting, and we don't have convolution semigroups. I mean, that's it. But it's a computation for Zn. So Bernoulli. Well, now that we did it for Zn, let's do it also for the diedral groups. Once again, I regard the diedral group as permuting the coordinate axis of Rn. And here the law, it's well, there actually is three Diracs at 0n, of course. And now there is a middle thing. So when n is odd, it's at 1. When n is even is at 2. Why? Because the diedral group, well, first we have the rotations, right? These have no fixed points except for the identity. But now the symmetries, there is a difference. Let's take a triangle. Okay, we have 3 symmetries. Each of them has 1 fixed points. Same goes for pentagons, everything. But now for the square, you have 2 symmetries with respect to the diagonal. So they have these 2 fixed points each. And 2 symmetries with respect to the axis, which have 0 fixed points. So when n is even, it's 50-50 for symmetries between 0 and 2 fixed points. And that's why we get this thing here. Here we get delta 1. Once again, well, this is just for finite truncation. Asymptotics are not interesting. Now, for the symmetry group itself, this is interesting, and we've seen this a few lectures ago. So first of all, the character counts the number of fixed points. The truncated character counts the number of fixed points, but among 1 up to Tn. And this guy follows the Poisson law. So how's the proof? Well, the simplest possible thing is to take T is 1, compute the probability at 0. So let's compute this probability. This means for the permutation to have no fixed points. And no fixed points, this can be computed by using the inclusion-exclusion. So you have your Sn here, there are permutations fixing the point 1, those fixing 2, those fixing 3, and so on. We're trying to compute some of the complement of all these guys. So to do, we take everything, we remove all these things, then we put back the intersections because we remove them twice, and so on. There's an alternating sum. That's the inclusion-exclusion principle. So you get all these factorials here, and that's the series of 1 over e, right? And well, now once you have this, so that's good. I mean, it's exactly the probability for the Poisson of 1 to be 0. It's a good start. Now you can further complicate this thing. So compute also the inclusion-exclusion when chi is k, you get this. So in the limit Poisson, of course. Also, you can pass to truncated characters, which means just your fixed points, you have to restrict the attention just from 1 to Tn, integer part, and you get Poisson of t. So very nice thing. Now finally, what we've seen also in lectures before is that this Poisson computation generalizes to the complex reflection groups. So these guys here, which means permutation matrices, but with non-zero entries, roots of unity of order S. And we get the so-called Bessel laws. So these Bessel laws are by definition compound Poisson laws with respect to the epsilon s being the uniform measure on the roots of unity. And well, this is really very interesting probability. And the terminology comes from the fact that, well, SIS1 is of course Poisson, is the symmetry group. At SIS2, where the group is the hyperoctahedral one, the measure is real because the roots of unity of order are 1 minus 1, everything lives on R. And the density is a Bessel function of the first kind. So in general, the density is a kind of weird thing and a kind of higher Bessel function of the first kind. So yeah, very interesting results. Now let's discuss now Lie groups. So well, you're not surprised. I mean, since for this case we got Poisson, here we can only get normal laws, right? So here are the formula shown now. Gaussian law parameter 1 or parameter t. I always need centered one, so that's why I have only a parameter. Importantly, this appeared here at the central limit theorem. That's why they appear all the time in real life. It's everywhere in real life there is a central limit theorem going on. And that's why you get all these normal laws. And now we'll be using the moment methods. What are the moments? Well, you can do a partial, that's your moment, do a partial integration. You get this recurrence. So the moments are double factorials. The convention double factorial is the number product of odd numbers when your k is even, otherwise it's odd. So now let's go for orthogonal group. The law of the character is asymptotically this normal of parameter 1 and it goes to infinity. So how to prove is here we don't have any more inclusion exclusion. I have to do something else or use this Brower easiness result. So what are the moments of chi? Well, these are by Peter Weil the dimension of fixed points. Now Brower tells you that these fixed points are actually the spans of certain linear maps associated to pairings. P2 stands for pairings. So P2 of k is pairings of 1 up to k. So now we can check. I mean, things T pi are not exactly linearly independent when t goes to infinity. Let's say we can compute their determinant, something like that, of the Gram matrix, and it's non-zero. So it's well known they are linearly independent. So here in the goes to infinity limit, you just have to count the number of pairings of 1k. So what's this? You have to pair one with something, you have k minus 1 choices. And once you have your pair, you have to pair the second thing with something k minus 3 choices. So it's k minus 1, k minus 3, and so on. So it's k double factorial. So chi has the same moment as the Gaussian law. Let's go back. Yeah. When t is 1, that's exactly k double factorial. So we're done. So this was for y, and now for and for the main character. Okay, we're not truncating yet. But the other classically groups, it's a bit the same. So same methods. I mean, easiness for you and also with Brower. To obtain a complex Gaussian law because the moments count the matching pairings of 1 up to k. What else do we have? I already told you that the stochastic groups are also easy, coming from pairings on singletons. So when you add the singletons, this spectral measures get shifted. And shifted versions of G1, G1, real and complex. And finally, well, the symplectic group is left. This is not exactly easy, but it's kind of super easy in some sense, technical, and we also obtain a normal law. So very good, we have here everything, only types. Let's discuss truncation. I mean, that's something very interesting because if you want to truncate these characters, let's go back here. So what was the main ingredient? It was Brower, of course, but first it was Peter Weil, okay, the moment of the character, the dimensional fixed points. That was part of the Peter Weil theory. We put a truncated character, this won't work at all. I mean, these are not, have to go far beyond that, and actually the formula for integrating over our group. Well, we can't get away just with these basic formulas like this. So let's integrate now. And in general, well, the idea is just that in order to integrate an arbitrary quantity like this, so these exponents as exponents are nothing at all, or bars, right? You have to always put bars there because we're unitary now. These are just coefficients of Peter Weil representations. So now for a representation, in particular for Peter Weil 1, we know that this integrals from the projection onto the fixed points. So let's just take a basis, dk basis of x by k. It's clear that everything will depend on that basis, right? Okay, so I have a basis, and I have to project to find the formula of the projection on that span of that basis. The idea is that that depends on the gram matrix of the basis, more precisely depends on the inverse of the gram matrix. So here's the formula. We sum over all elements of the basis. That's the inverse of the gram matrix. Okay, gram matrix and inverse. And then we put the coefficients of the basis elements. These are the coefficients here and here. So that's all it follows from what I was telling you, some linear algebra. Now in the easy case, in the easy case, we have a basis. I mean, that easiness means exactly that. You have a basis formed by partitions of these guys. So the formula simplifies in the sense that, well, the gram matrix is very simple. If you take two partitions, this entry of the gram matrix is n power number of blocks of the join. So you put pi into you superpose them, you count the blocks. That's all. So the gram matrix is just powers of n. Okay, so these are the exponents. And what else changes? Well, of course, the coefficients. So these delta guys, let's go back. These were just the coefficients of sigma in the basis. But our vectors are something like this. So the coefficients are Kronecker symbols. They're usual Kronecker symbols. So something very simple. Finding the integration of over an easy group. Just some elements of this Weingarten matrix. Which Weingarten matrix is the inverse of something of matrix of type like n3 and 5 and 7, and it's a matrix formed by powers of n. It's very, very simple to run on a computer. I mean, that's there's a lot of computers for doing these kind of things. So now with this, let's go back to characters. So that's a truncated character, right? G11 up to some GSS. S is typically an integer part of Tn. So if you compute here, you expand right by Weingarten, all that, and get a trace. So trace, that's the gram matrix G, and that's the Weingarten matrix. And this all depends on the category. Asymptotics can be worked out, no problem. And you reach to, what do we have? Let's go back. So we knew, for instance, for n we get G1, the truncated character will get BG2, same here for the UN, gonna be the same here. So finally, as a final result, let's just select ON, and HNKN, which are some of the 4 main groups. You see we have here real complex and discrete continuous. So these are the 4 main groups. And the laws for truncating characters when it goes to infinity are real Bessel, complex Bessel, real Gaussian, complex Gaussian. And of course, you have, because this measure from semigroups, there's some independence in them there, you can work that out, everything. So yeah, this follows by using these formulas, and of course in the discrete case we don't need all that, you just have the inclusion exclusion principle, but yeah, that's somehow the conclusion, that's the main result, and you can of course build enormously enormous quantity of things that can be built on this, but that's the main result. I think it's a very nice introduction to a way of yeah, getting introduced to probability on compact groups. It's we're motivated both by probability and by algebra. So in what we said in all this course, we're mainly motivated by algebra, right? So we compute that law because we want the moments, which are the dimensions of the Tankian categories, the so-called Poisson series, if you want. But there's also a lot of probability, like definitive theorems, things like that. So it's a joint thing. I mean, it's the same thing, probability and algebra. And that's the way of getting started computing these laws of characters. So hope that you like it. And for more advanced stuff, yeah, check the channel here. We have many more advanced courses as a continuation of all this. Bye-bye.